I'd like to talk about how we can graph functions using transformations. That is, we're going to start by looking at graphs that we're familiar with and use transformations to figure out what the new graph would look like in an efficient way. In this video, I will assume that you know the look of the graphs that I talked about in a previous video, a library of functions. The functions that I'm going to assume that you're familiar with are y equals x squared, y equals x cubed, y equals the square root of x, y equals 1 over x, and y equals the absolute value of x. We'll call these functions our parent functions or basic functions, and their graphs will be called our parent graphs or our basic graphs. We'll use these throughout the video to illustrate the points. So let's jump in. Let's start with this. Graph y equals x squared plus 3. Now notice it seems to be related to this function right here, our y equals x squared graph. It kind of looks like that, but we have this plus 3 added to it. So what does that do to the graph? For this example, we'll just plot a few points and see what we get. So I'll put in values like -3, -2, -1, 0, 1, and 2. And if we substitute -3 in, we'll get -3 squared is 9, plus 3 is 12. -2 squared is 4, plus 3 gives me 7. -1 squared is 1, plus 3 gives me 4. And I can continue substituting in the values, and you'll find that you get 0 gives me 0, 1 gives me 4, 2 gives me 7, and 3 gives me 12. So if we were going to sketch this graph, I'm going to just mark my grid here. We'll go by 1s in the x direction, and let's go by 1s in the y as well. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And I'll plot a few points. -3 gives me 12, and +3 gives me 12. I'll put both of those on at the same time. -2 gives me 7, 2, which is about right here, and +2 gives me 7. -1 gives me 4, and +1 gives me 4, and at 0, the value is, whoops, I put in 0. We know that's not right. 0 gives us 3. So we'll pop that in. So our graph looks something like this. And I hope that this looks familiar to you. I hope you recognize that this is the graph of y equals x squared, this one, that's just been shifted up 3 units. And I hope that's no surprise to you, because look right here. Each of the y values in y equals x squared is being increased by 3. And if we increase all the y values by 3, our graph is raised up by 3 units, or moved up by 3 units. So suppose we were going to graph this one. Graph, and it was y equals x squared minus 4. What would your best guess be? I bet you know what it would be. We would have a function. The parent graph is y equals x squared, but now the y values are decreased by 4. So that means we're going to shift the graph down 4 units. And when we do that, our vertex would be down here at -4. And then I draw the exact same shape as I would in my parent graph, a parabola. And it's complete. Now, I don't have the details put in. I don't have the x-intercepts listed. But as a nice rough sketch, we have it, and we have it quickly. That's going to be the goal for this video. Can we come up with a pretty good sketch relatively quickly for each of these problems? The nice thing is that the shifting graphs up or down work the same for all functions. If we take a particular function and add a constant to it, the parent graph would be shifted up or down appropriately. Let's write the summary of that. So here it is. Given a function y equals f of x and a constant k that is greater than 0, we have the following transformation. Y equals f of x plus k shifts the function up k units, and y equals f of x minus k shifts the graph down k units. And notice it didn't say anything about it being y equals x squared. This is true for any function. So if we had a problem that looks like this, we're to graph y equals the square root of x plus 7, for example, and we just wanted a quick sketch, we would think about our parent graph first. Y equals the square root of x. And do you remember what it looks like? Here it is. It's our graph that looks like this. It's actually half of a parabola that's on its side, but that's our parent graph. Now we're looking at this function which says, hey, shift it up 7 units. So our graph now would look like this. Make sure you label 7 appropriately, and I would draw my function. And it's done. If somebody needed more detail, then you could go ahead and plot some points. But often what we need is just a quick sketch, and this would do. Let's move on. Let's sketch the graph of y equals the quantity x minus 3 squared. Notice the distinction between this and our previous examples. In this one, the minus 3 is right here with the x. This 3 is being subtracted from x. It is not being subtracted from the entire function. Let's see how that makes a difference when we're sketching our graph. So I'm going to do what I did previously, and that is just plot a few points. After we figure out what this kind of a transformation does to a parent graph, then we won't need to plot any points again. I'm going to put in integers from 0 to 6. So 0, 1, 2, 3, 4, 5, 6. And we'll do our calculations. So if we substitute 0 in, we'd have 0 minus 3. Make sure you're careful to put it in parentheses and square it. That would be positive 9. Similarly, I would substitute in the other values. 1 would give us 4. 2 gives us 1. 3 would give us 0, 4 gives us 1, 5 gives us 4, and 6 would give us 9. So let's see what this looks like. 0, 1, 2, 3, 4, 5, 6, and I need to go up to 9. So if we plot a few these points, we would have 0, 9, and 6, 9, 1, 4, and 5, 4, 2, 1, and 4, 1, and 3, 0. And we see that we have a graph that looks like this. It looks like our y equals x squared graph that has been shifted right 3 units. Sometimes people find that surprising. Notice right here, this is a minus 3, and we can see based on the points we plotted that it's shifted right 3. So what would be your best guess if we were going to sketch the graph of y equals x plus 5 squared? Do you recognize it would have the same parent graph? It would be the parabola, our y equals x squared graph. But notice over here, when we had a minus 3, it shifted right 3. So with a plus 5, can you guess what it would look like? In fact, it is our parabola that will be shifted left 5 units. In fact, we move the graph over to the value that would make this quantity equal to 0. -5 makes this quantity 0, so -5 plays the role that 0 did in our parent graph. So let's sketch our graph quickly here. I would just have my parabola going this direction. It would cross the y-axis, but not until you get way up to 25. And I have a rough sketch. The same idea would hold for any function. If we add or subtract a number to the x value, the parent graph will be shifted left or right. Let's write the summary. So here it is, given a function y equals f of x and a constant h greater than 0, we have the following transformation. Y equals f of x plus h would shift the graph of f to the left h units, and y equals f of x minus h would shift it to the right h units. And again, notice it's independent of the function that we're talking about. Let's look at this example. We're going to sketch the graph of y equals 1 over x minus 2. Make sure you make note of the fact that the 2 is being subtracted from the x. It's not being subtracted from the function itself. Like in contrast, it's not y equals 1 over x minus 2. You need to make sure when you're looking at these problems that you pay attention to where the minus 2 is. So in this one, the minus 2 is being subtracted from an x. That means we have a horizontal shift of our parent graph. Do you remember that the parent graph for this one is the graph of y equals 1 over x? That looks like this. So we're going to take this graph and now shift it to the right 2 units. Remember, when it's subtraction, we shift it to the right. So let's do that. I'm going to draw my grid, and I'm going to pick this graph up right here and shift it to the right 2. Now, here's an important detail. Remember that there are asymptotes when we're talking about the y equals 1 over x graph. We have a vertical asymptote here and a horizontal asymptote here. So I'm going to draw in the vertical asymptote first. This vertical asymptote that was at 0 is going to be shifted to the right 2. So let me come over here and do that. Instead of having a vertical asymptote here, I'm going to shift right 2 right here. I'm going to draw my vertical asymptote. I'm going to label it at 2. My horizontal asymptote does not, it does get shifted right, but when you shift a horizontal line right, it doesn't look like it changes at all. So we still have the same horizontal asymptote. You don't really need to draw it if it's on the axis. It's hard to see a dashed line on top of a solid line, but you would definitely want to include that vertical asymptote at 2. So now let's just draw the rest of the curve. We know that it looks something like this. It's approaching this asymptote and this one. And on the other side, I'm going to put this point in and draw my branch of what's called the hyperbola. And I have my rough sketch done. Now, if you're not 100% sure that you have it shifted the right way, let's look at this in relation to its domain. Remember that the domain of this function would be all real numbers except 2. 2 would make the denominator 0. And notice our vertical asymptote is at 2. So it gives us some confidence that we did it correctly. Let's move on to our next transformation. Let's sketch the graph of f of x equals the opposite of the absolute value of x. I hope you recognize that the parent graph or parent function would be f of x equals the absolute value of x. Do you remember that it is our graph that looks like this? Looks like a V with the branches of the V having slope 1 and -1. But let's just plot a few points and see what this looks like. If you plotted some points, we'll put in -3, -2, -1, 0, 1, and 2, and 3. If you pop -3 in, let me do it here in scratch paper. Remember the negative sign would be outside because that's our function. And we're substituting in -3. So that's the opposite of the absolute value of -3. So our result is just -3. Similarly, -2 would give you -2, -1 would give you -1, and 0 would give you 0. When you pop in positive values, like 1, we would be taking the opposite of the absolute value of 1, and that would be just -1. Similarly, 2 would give you -2, and 3 would give you -3. And if we plotted these points, we would find that we have something that looks like this. -3, -3, and +3, -3. -2, -2, and +2, -2. Similarly, -1, -1, and 1, -1, and 0, 0. And our graph looks like this. And notice our function has been reflected about or across the x-axis. And in fact, that will be the case for any function. If you put a negative in front of your parent function, the graph will be reflected across the x-axis. Let's write that in general. If y equals f of x is a function and we know what its graph looks like, then y equals the opposite of f of x can be graphed simply by reflecting the graph of x across the x-axis. That means we could graph something like this very easily. We know the parent graph, y equals the square root of x, would just look like this. I'm over here on my scratch paper thinking about it. Now I could come back over here and reflect that across the x-axis. So that means I would draw it below the x-axis, and my function would look like this. And it's done. And again, remember, we're just coming up with a rough sketch. If you needed it to be a little bit more precise, you could plot a few points. Let's look at our next transformation by looking at this example. Sketch the graph of y equals the square root of the opposite of x, and notice that the negative is inside the square root. In fact, the negative is in front of the x. So let's plot a few points and see what this looks like. Notice our domain will be something we should take care with. We can certainly put in 0, and the square root of 0 would be 0. But now when we put in 1, notice we would be talking about the square root of -1, which is I and not real, and of course not on our graph. So we can't put in 1. But what could we put in? How about -1? If we put in -1, we would be taking the opposite of -1 underneath that radical sign, and that would be the square root of 1 or 1. I could substitute in now any negative real number. Now I could put in -2, it would give me an irrational result. So let's just jump to -4. So that our results will be rational. If we put in -4, remember it'll be the opposite of -4 underneath the radical sign. So that's the square root of 4 or just 2. Similarly, if we put in -9, we would get 3. And when we graph this, we would see that we have this 0, 0, -1, 1, -4, 2, -9, 3, and our graph looks like this. Notice it looks very similar to our parent graph, but it is reflected across the y-axis. And that's the key when you put a negative in front of your x. Let's write that out in general so that you can see what I'm saying. Given the function y equals f of x, if we wanted to graph the function y equals f of the opposite of x, we would just take the graph of f and reflect it across the y-axis, and we would have our new function. So let's look at another one. We can put the next one right here on this same page. Let's sketch the graph of y equals negative x cubed. And I put parentheses around that negative x. So we see that that negative is right in front of the parentheses. Right in front of the x. So I'm thinking about this being the reflection of y equals x cubed across the y-axis. Let me remind you what y equals x cubed looks like. Here's our parent graph right here. It looks like this. So when we reflect that, now come back over here, across the y-axis, this part right here would be reflected across, and it would exist over here. So let's come over here on this graph and draw it. So it's right over here. And this part here gets reflected across the y-axis, and so it would come over here. So in my graph, I would come here, and it would look like this. And if you're thinking, well, that looks a lot like y equals negative x cubed without the parentheses, that's correct, because y equals negative x cubed with the parentheses is completely equivalent to y equals the opposite of x cubed without the parentheses. So for this particular graph, the reflection across the x-axis and the reflection across the y-axis gives you the same result. But that will not be the case in general. For our next transformation, I would like to look at the graph of y equals 3 times the absolute value of x. In other words, I want us to look at what happens when we multiply a function by a constant. And for this one, you can see I already have the parent graph drawn. I have y equals the absolute value of x drawn on the grid. So let's plot a few points and see what y equals 3 times the absolute value of x would look like. So I'm just going to put in a few points. We'll put in -2, -1, 0, 1, and 2, and see if that's enough to let us know what the graph is looking like. So if we put in -2, we would have y equals 3 times the absolute value of -2, which of course is 3 times 2, or 6. So -2 gives us 6. Pop in -1 and you would get 3. 0 would give us 0. 1 would give us 3, and 2 would give us 6. So if we plot these points, I would have -2, 6. Notice it's up here. Similarly, 2 is at +6 as well. -1 is at 3, and 1 is at 3. And 0, 0 stays right where it is. And here's what the graph looks like. It looks like the same picture, but stretched out by a magnitude of 3. Each value of y has been multiplied by 3. So this one right here that was at 1 is now at 3. This point that was at 2 is now at 6. This point that's at 5 would be way up at 15. So it stretches by a magnitude of 3. Just because I have this already graphed, let's just do one other thing. Suppose I were to graph this. sketch the graph of y equals, I'm going to come over here, y equals 1/2 times the absolute value of x. If you plotted points for this particular function, I could still put in -2, -1, 0, 1, and 2. Notice if you put -2 in, you would get 1. -1 would give us 1/2. 0 would still give us 0, 1 would give us 1/2 again, and 2 would give us 1. So the points would look like this. Let me just graph it here. And it looks like this. So all of the y values that were on our parent graph are now half as high. So multiplying by 3 stretched it by a magnitude of 3. Multiplying by 1/2 compressed it by 1/2. And let's write that up in general. So given a function y equals f of x, if we multiply the function by a constant, the function is stretched or compressed vertically by a factor of that constant that we multiplied by. If the constant is bigger than 1, it's a stretch. If the number is between 0 and 1, then it's a compress, as you saw in this example. Let's do this example. I'll graph the parent graph on the grid. It will be easier for comparison for us to see what y equals 7 times the square root of x looks like. In other words, I'm saying we're going to put y equals the square root of x on our grid. So it looks like this. Now remember, multiplying that function by a constant 7 means at any point the y value is now 7 times as high. Ignore my phone that's ringing off in the distance room if you can hear that. And let's see, right here, we'll go up 7 times as high. Notice it's not even labeled, but whatever this length is right here, we know on y equals 7 times the square root of x, it would be 7 times as high. So let's say that's 1, 2, 3, 4, 5, 6, 7. It would be up here. It's very stretched out. So right here, how about this point right here? 7 times as high as this. 1, 2, 3, 4, 5, 6, 7. It's way up here. And of course, it's 0. If you stretch it out by 7, you're still at 0. So we end up with a graph that is very stretched out, looking like this. We have one more transformation to talk about. For this next transformation, I'm going to show it a little bit differently. I'm not going to start with one of our parent graphs that we have in our library of functions, because for those functions, it's harder to see this transformation. So I'm going to just graph y equals x squared minus 6x first, and then we'll use that as our base graph, and we'll transform it, as you'll see in just a minute. So we're going to graph y equals x squared minus 6x. I've already plotted some point or came up with some ordered pairs that are solutions. You can confirm that those are correct. So if I were to graph this, it would look like this. I'm going to put in 0, 0, and 6, 0, 1, negative 5, and 5, negative 5, 4, negative 8, and 2, negative 8, and 3, negative 9. Just counting, making sure I have that right. And the graph actually looks like this. It's actually another parabola. It'd be nice if I had actually gone through the points, but it looks like this. So maybe you can just take me at my word that this is what y equals x squared minus 6x looks like. But here's how I want to transform it. Here's our transformation. we're going to replace x with 2x. So now we're going to graph y equals 2x squared minus 6 times 2x. So we're going to see what happens if we take a function and replace the x with 2x. So here we go. Let's plot points. I'm going to still stick with 0, 1, 2, 3, 4, 5, and 6. 0 will still give me 0. 1, if you pop 1 into that function, notice you'll have 2 times 1 squared minus 6 times 2 times 1. So there's the arithmetic. So we have 4 minus 12, or negative 8. If we substitute in 2, we'll have this, which is 16 minus 24, also negative 8. We substitute in 3, and we have 2 times 3 squared minus 6 times 2 times 3, and we have 36 minus 36, and we're at 0. That's interesting. Let's plot these on our grid over here. So I still have 0, 0, and I have 3, 0. I have 1, negative 8, and I have 2, negative 8. Now I'm not such a fan of plotting 4, 5, and 6. I want to erase those, and let's make a different choice for substituting into the function. Let's put in something between 1 and 2 and figure out what's happening in between 1 and 2, because I don't think it's going to go straight across. So let's put in 1.5, or 3/2. So we're popping 3/2 into the function. We have 2 times 3/2 squared minus 6 times 2 times 3/2. And you'll notice that this will be 9 minus 18, or negative 9. So at 3/2, we're at negative 9. Let me put that on my graph. 3/2 is at 1.5 right here, and we're down at negative 9. Do you see that the graph seems to look like this? Let me sketch it. It is still a parabola, but notice it's been compressed. And that is, in fact, what's happened. This graph, the original graph of y equals x squared minus 6x, was compressed toward the y-axis. I think I may have said x-axis earlier. Compressed toward the x-axis by a factor of 1/2. In fact, it's compressed by a factor of 1/2. Let me say right here. Let me do one more just to tell you how this works. If we were going to graph y equals 1/2 x squared minus 6 times 1/2 x, in fact, replace the x with 1/2, it's actually going to be a stretch with respect to the y-axis. So we're going to take the reciprocal of this number right here, and that gives us our stretch or compress factor. So we stretch by a factor of 2. So here's how it looks. This point would stay right where it is, because remember, we're stretching with respect to the y-axis. And the black graph is our original one. This one is stretched out, so instead of being here at 3, negative 9, it's going to be at 6, negative 9. This point that was at 6, 0 is now going to be way over here at 12, 0. And our graph looks like this. Very roughly. So let's write up in general what happens if we replace x with a constant times x if we're transforming functions. So we have this in general, given a function y equals f of x and a constant a that is greater than 0, we have the following transformation. Y equals f of a times x is a graph that will be a horizontal compress or stretch compared to the graph of y equals f of x. We take the reciprocal of a, and that's our stretch factor or our compressing factor. So if a is 2, you take the reciprocal and you have a half, and you compress the graph toward the y-axis. And if a is between 0 and 1, like a third, you take the reciprocal and you have a 3 and you stretch it out by a magnitude of 3. So those are our transformations. Let me take you to the next page where we have all of the transformations summarized. Here they are.